that any chemical reaction, A yields B, we would also expect to see the reverse reaction, which is B yields A, right? Both reactions should occur. We'd call one the forward reaction, one the reverse reaction. It's actually arbitrary which one you call the forward reaction, right? Like, it doesn't really make a difference. You could call B forms A the forward reaction if you wanted to. It's an arbitrary kind of decision what you call the forward. But all the same, we're going to call this the forward reaction, and we'll call this the reverse reaction. Such that if we wanted to, we could keep track of the concentration of A, which is the reactant we start with, and we could keep track of the concentration of B if we felt so inclined. And if we started out with just A, we talked about this yesterday, what's going to happen? If we start out with a bunch of A and we start out with no B, which reaction is going to happen exclusively at the beginning? A isn't a reaction, it's a reactant in this case. But the forward reaction, which means that we're going to use up A, and while we're using up A, we're going to produce more of B, kind of that sort of thing. But that means that slowly but surely, this reaction's got to slow down, because we know reactions slow down as the concentration of reactant decreases, right? Which means the forward reaction is going to slow down, but as the forward reaction is slowing down, the reverse reaction is going to speed up, which means we'd actually expect to see this turn around. And that's going to happen over and over again, but it's going to asymptotically approach a steady state. And where that steady state is depends on a lot of things. We said it depends on the nature of the reaction. Which of these reactions is faster than the other? If you knew the K value of both reactions, you could act at these conditions, you could predict where these would end up. We talked about that yesterday. But we eventually reach what we call an equilibrium, which is a steady state. And this is where the concentration of the species become constant. And it's not actually that they're constant, it's that as quickly as A is being used up to make B, at the exact same rate, B is being used to make A. In other words, this is the point where the rate of the forward reaction is equal to the rate of the reverse reaction. That's our definition of what we call a dynamic equilibrium, or a chemical equilibrium, is that it's the point at which the rate of every reaction involved in a series of reactions, forward and reverse, are all equal to each other. We actually said at the end of yesterday that it doesn't actually matter if this is a one-step equation or a reaction, or a two-step reaction, or a 55-step reaction. Mathematically, there has to be some combination of concentrations of everything where all of the reactions end up happening at the exact same rate. And once the system reaches that concentration, it's going to lock in and everything's going to get steady. And we call that steady state equilibrium. How's that feel? Not too bad? Which? Forward. Sorry. We don't say shut up. I mean, I say shut up. You don't say shut up. Shut up. Anyway. Just laughing with you. That's what my parents used to say when people would laugh at me. Anyway, we'll move on. So, how's that feel? Not too bad? Feels okay? All right. Now, we actually write this a different way, which is we use a little double arrow to indicate this. Instead of writing both the forward and the reverse reaction, the convention in chemistry is that we say that this reaction can go in both directions. So rather than write both reactions out, you will see this kind of double-headed arrow, and it isn't drawn like this, sort of as a single arrow with two heads. The convention is always kind of this thing. That's what our equilibrium arrow looks like. Yeah? I wasn't there. So I don't know. But yeah, no, you'll be shocked to hear that the International Union of Pure and Applied Chemistry didn't invite me to the meeting when I was negative 20 years old, which is rude, right? I should go beat up IUPAC. It's all of them. Hear that if you're listening, IUPAC, be afraid. So for a simple reaction where everything is first order, we can easily formulate an equation to define the state of the system at equilibrium. And again, we're going to quickly review what we did yesterday, which is we'd say that if we were looking at the forward reaction of this, we'd say that the rate of the forward reaction would be equal to what? Okay. Some constant K. We'll say K for forward. And what would it depend on? Concentration of A. And in this case, to what exponent? If we assume this is a one-step reaction? 1. N times concentration of B. Okay. And as we saw yesterday, we can actually assume that every reaction is a one-step reaction when we're doing these. So the rate of the reverse reaction would be equal to some other constant K. We'll call it Kr for reverse. And it would depend on what two concentrations? It would depend on the concentration of C and D. And then we'd say, at equilibrium, the rate forward equals the rate in the reverse direction. And if those two things are equal, what then can we say? If the forward rate is equal to the reverse rate, then how could I rewrite this equation? We could say Kf times concentration of A times concentration of B is equal to Kr times concentration of C times concentration of D. Very good. And now, if I wanted to, we could arrange this a million different ways, but by convention, we're going to put all of our concentrations on the right and all of our constants on the left. What would I have to move to do that? I'm going to put my, very good. I'm going to put my Kr on the left, and to do that, I have to do what? Yeah, divide it by Kr, so it'll be Kf, that's a terrible looking F, let's just try that again. Kf divided by Kr, and on this side we would have concentration of C divided by the concentration of D over concentration of A times concentration of B. Now, you're never going to have to do this math again. But just to show us on the next page where that comes from, that's how we came about this. That's where this comes from. And I'm just going to say that we're going to combine all constants into a single one.
Is that one uppercase?
Yeah, by convention we use an uppercase K. I put a C there, which stands for concentration, so the concentration constant. You'll see Kc, you'll see Keq, you'll see a few other things, so I like to try to mix them up so you get exposed to all the various different ones, and then you'll see ones that are specific to a type of reaction. So if we're talking about solubility, you'll see KSP for solubility. Actually, I don't know what the P stands for on that. Or Ka for acids, or Kb for bases, or whatever. So they use the subscript to kind of help you identify what you're talking about, but it's consistently a letter K, used an uppercase K used for equilibrium constants. So by convention, we use a lowercase k for rate constants and uppercase K for equilibria. How's that feel? Not too bad? Again, you're never going to have to recreate that math. I want to show you where it comes from. In general, then, in a system at equilibrium at a fixed temperature, and I should say and pressure, the product of the equilibrium concentration of the products divided by the product of the concentration of the reactants, each being raised to the coefficient of the substance in the equation, must be equal to a constant. Listen, that's a lot of words, right? It's not nearly that bad. We just say this. If we had A plus B reacting to form C and D, and I've put little coefficients in front because we want to show that actually it doesn't have to be to a coefficient of 1. We would define the equilibrium constant K as, by convention, which one do we put on top?
Product.
Yeah, we do products on the top. And reactants on the bottom. You don't always even put one. I'm just putting a K. And we're going to do the concentration of C to the exponent C, the concentration of D to the exponent D, whatever it might be, the concentration of A to the exponent A, whatever it might be, and the concentration of B to the exponent B, whatever it might be. I was going to make this a retread lesson. I ended up changing that. But just a reminder that even though we can't just plug the exponents in the rate law, you have to find out what the slowest step is, because at equilibrium, every step of every reaction is going at the exact same rate. There isn't a slow step. The whole overall reaction is the slow step, so you can just use the coefficients. Does that make sense? Rate laws, you have to worry, hey, what's the slowest step? Here, there isn't a slowest step. They're all going at the same rate. That's the definition of equilibrium, so you can just use the overall equation and go. Does that feel okay? All right, can we do a real example? All right, you guys are going to do it. Here's our first reaction, and it is, for some reason, devoid of subscripts. I swear I didn't make it that way, but that's okay. It is C2H2. Bonus points if you can tell me what the name of that is. Reacting with oxygen, 5 C2H2s plus 5 oxygens. Sorry, 2 C2H2s plus 5 oxygens, yielding 4 carbon dioxides and 2 waters.
Is that ethyne?
Sorry?
Is that ethyne?
That is ethyne. All the bonus points. I mean, this isn't graded, so that doesn't mean anything, but you can brag. You'll be like, I got all the bonus points. All right, so write me a K equilibrium for this, and again, there you go. So go ahead and write that for me. No, I'm coming to make a coffee. Would you like me to yell at you?
I honestly thought I was prepared if I'm being honest.
God damn it!
Did you see my shoulder shuttle? No. Did you hear my voice? Did you hear my voice?
Oh, yes, we have. Let's do it Wednesday. Whatever on that. I'll do it Wednesday. Whatever on that. You're not the only council member. All right, what do we get? What is this? You got. Nasina, you want to give this to me?
Sure.
All right, give it to me.
So at the top we have concentration of CO2.
Very good.
So top one.
Okay.
And then concentration of H2O. To part two.
Very good.
Over concentration of C2H2.
Yeah.
To part two.
Yeah.
And then concentration of O2 to part five.
Awesome. Okay, beautiful. That was great. How's that? Not so bad, right? Looks good. Okay, now the thing is this. If we let a reaction, or more to the point, if we measure the concentration of each species at equilibrium, we can calculate the actual value, calculate the value of K. Does that make sense? If we actually knew all of the concentrations at equilibrium, then we could determine the constant K. Yeah.
Is there a better symbol for concentration?
Sometimes they use C for concentration.
But drawing two parentheses every time. It's a little
Did you use like M?
too much.
Sorry?
Did you use M?
That would be like if you calculate the grams of, which is like clumsy, right? It's not wrong, but it's a little clumsy. It's sort of torturing the English language. And listen, I'm not saying English doesn't have it coming. You know, you still want to be gentle with it.
Do like equilibrium constant, like the thing have a unit?
Ah, of course they do. Now, what does the unit depend on as it happens? It's going to be different for every reaction, right? Because if you look at this one, it's going to be like molar to the fourth times molar squared, so that's like molar to the sixth, divided by molar squared and molar to the fifth, so it's actually going to be molar to the -1, right? And that's assuming that you just treat molar as a unit overall, or if you treat it as molar CO2 times this, but we tend to just say molar.
So it's going to be molar something.
Yeah, that's right. But it's going to totally depend on the type of reaction. So with that in mind, here we have an equilibrium of phosphorus pentachloride being in equilibrium with phosphorus trichloride and chlorine gas. Go. I want to know the actual value of KEQ. So you're going to have to write that law of mass action equation, right? You're going to have to write that equation, and you're going to use that equation. All right, smarty pants, good for you. You're going to use that equation to tell me the value of K.
What did you do?
She's just already done. And she was smirking at me. She was giving me a smirk. Like, you're wasting my time, Orlando. Which I'm here for. No, listen, I don't disagree. I don't disagree at all. Can I tell you something? I am so excited for this cup of coffee. I feel like a small child on Christmas morning right now. Sorry? For now, eventually, there are some calculus. There's some calculus that can be done to account for temperature in your K value. But for the moment, we understand that the rate of a reaction depends on temperature, which means the rate of all the reactions are going to change if temperature changes. So a K value is only valid for a given temperature and pressure. You change the temperature and the pressure, K value is going to change. So it doesn't factor into your math, but it factors into the fact that your math is only valid. If you then went to use that K value, it's only going to be meaningful and it's only going to do valid predictions for you if you do it at this same temperature. Did that answer your question? It was a good question. Oh, didn't disappoint, team. Didn't disappoint. Solid cup of coffee. All right. Everyone got this? Do we have calculators? Est-ce que vous avez des calculatrices? C'est nécessaire pour toutes les leçons dans cette unité. Oui. Oh, oh, oh. Oh, you need your calculator.
I love
Don't
the
judge
laugh
me.
that you do at the end.
I know. Does it make you think, am I in Paris right now? What is going on? What if I came in one day with like a scarf and a beret and a baguette? Just noshed on my baguette while teaching, which is, I assume, what the French do. A small dog. What else? What are those stereotypically French things? I could be really in shape, but not like showy in shape like Americans. Just like very just very trim.
An obsession with croissants.
Yeah, croissant. Oh, I love croissant. You ever had like a good pain au chocolat? It's like a chocolate croissant. Okay, let me tell you right now. My wife and I spent 12 days in Paris for our 10th anniversary. It was lovely. It's great. Would recommend. Great trip. Paris is a beautiful city. But we rented the world's smallest apartment. It was like the size of, I don't know, you shove 3 of these desks together. That's about the size of this apartment we rented. But it was over top of a bakery called Café de la Poste. I'd go down every morning, and in my worst French, which is also my best French, unfortunately, I would order an American coffee, Café Americain, and a pain au chocolat. And it's like this chocolate croissant, and oh my gosh, just the most delicious thing. That's the way to start your day. And again, you know when the time to travel is? When you're young. It's cheaper. You just got to pay for yourself. You can stay in youth hostels. Way cheaper. Time to do it. Yeah, youth hostels are like hotels for young people, but they're often like dorm style, right? So it'll be like they'll often be like like 30 young women in one like shared room with like bunks and whatever, and then there's some of the supervised. So you're not like staying in like the highest like end hotel, but it's cheap, right? So you can get around relatively cheaply. I think you start being creepy by your late 20s. And I think at a certain point they stop allowing you. But like when I was in my teens and 20s, like that's how we traveled because you could afford to. Yeah. Hostels.
So could you still go if like you were too old and just be like, I'm ethical, or is it like specifically?
I don't even know. Like I don't know. Like I make enough money. Well, I work for a hotel now, so I get like so I can actually get a hotel room for the price of like a hostel now, which is basically why I keep my hotel job. I get cheap hotel rooms. And then I'm so busy I never get a chance to use them. But in theory, I can be like, man, I can travel cheaply. Greg works at the hotel, and he just did a trip to New York City with his buddies, and I think for like all 5 of them, the whole trip cost like $300 or something.
Wow.
Yeah. So they were there for like 6 days. So long story short, get a job working at a hotel restaurant, get cheap hotel rooms. It's a good gig. My trip to Switzerland, everything was so expensive I couldn't afford to buy anything, but the hotel room came with free breakfast, so I was like, oh, I'm going to load up at breakfast. I'm going to eat so much friggin' breakfast, they're not going to know what hit them. And all the Europeans who eat like 3 grapes and like a little pastry for breakfast, and I'm like, oh no, I'm fueling up for the day. I think they were ashamed of me, but that's okay. I can live with that. All right, what's the law of mass action here? What am I writing? The equilibrium constant will be equal to concentrations of what?
Concentration of PC,
Yeah.
and concentration of chlorine gas.
Chlorine gas, good.
And then concentration of phosphorus.
Excellent. All right. So there we are. Now, can I actually calculate this as given values? Well, as it happens, we've measured all these. What is the concentration at equilibrium of PCl3? 0.25 molar. What is the concentration of Cl2? And what is the concentration of PCl5?
0.1.
0.15. So all I have to do then is do what? Sub those into the equation. 0.25 molar times 0.25 molar divided by 0.15 molar. So I don't know. This is going to be 0.0625, and then multiply that by, God, I don't even know. What is this?
0.4.
What is it?
0.416, so rounded off to 4.42.
Yeah, very good. Okay, so 416 will round to 0.42. Good. And our unit will be, well, in this particular case, that molar will cancel with that molar, and our unit remaining will be molar. Okay. That won't always be the case. All right? And now we could write if we wanted to, we could rewrite this and say that the concentration of PCl3 multiplied by the concentration of Cl2 divided by the concentration of PCl5 is going to be equal to 0.42 molar at all times at equilibrium. Any equilibrium you set up for this will end up equaling that. Yeah.
Why is it like a convention to put the products at the top and the reactants at the bottom?
Because it's important to be consistent. And when it's first derived, we derive it like we do here and like we did here. And so the math just kind of naturally lends itself to working it out that way. And that's like, why do we drive on the right side of the road? There's nothing magical about driving on the right side of the road, but it's important that everyone do the same thing, right? Otherwise we bump into each other. So likewise, it's important to have a convention where everyone does the same thing so we know what to do when we see something like this. So that's the convention. There isn't really, there's not a specific reason for doing so.
So if you did the opposite, you just have like a different,
You would actually have, so if you did it backwards, don't write this, right? But if you did this and said, oh, K is equal to concentration of A times the concentration of B divided by the concentration of C times the concentration of D, what you've actually found is the equilibrium constant of the reaction as written this way, which is the exact same reaction. Because, again, equilibrium means that it runs forward and reverse. So just by, you would still have found meaningful information. It would just be backwards to what somebody reading the equation like this would expect. Did that answer your question? It was a fair question. It's a good question. I hope my answer made some kind of sense. All right. How's that feel? Straightforward, right? Pretty reasonable. But this is a really powerful tool because it means that for any reaction that we regularly do, bless you, we can, in the lab, perform that reaction under standard conditions, measure the concentration of everything, and then we can have a fundamental understanding of that reaction, right? Because now, and we're not going to get into doing the math of this today, we'll do it in a day, but now I could actually tell you the starting conditions, and with a little bit of calculus, or the way we're going to do it in this course, a little bit of quadratic manipulation for simple enough reactions, you can actually figure out what the concentrations will be at equilibrium. You can make predictions. Does that make sense? Yeah. This is specific to that reaction at that temperature. If you change the temperature, the K value will no longer be predictive. And the more you change the temperature, the more wrong it'll be. Does that make sense? If you change the temperature by a degree, this is going to be a really good approximation. If you change it by 50 degrees, this will probably be way off. Did that answer your question? Good. Okay. Now, as a great segue, your question, we're going to lead into something called Le Chatelier's principle. I have this long-standing tradition of making sure we include a photo of anyone something is named after. So let's find ourselves Le Chatelier. Like the actual guy. Henri Louis Le Chatelier. Who I think looks an awful lot like John Cleese. Do you know John Cleese? Like from Monty Python? Do you not? Oh, Monty Python is so funny. I guess that's a matter of taste, but Is every picture just him in Holy Grail? Come on now. Oh, that's because I searched for Monty Python instead of John Cleese. Hear me out. Huh? No, you can't see it? Look again. I'm just saying. Anyway, that's the mustache I should grow. So this is our buddy Louis Le Chatelier, Henri Louis Le Chatelier. And he studies reactions, and what he finds is that when a system is at equilibrium, so a system has reached equilibrium, if you introduce a change to that equilibrium, that's going to make the equilibrium be out of alignment, right? Which means if you make it unsteady, now everything's going to move again, right? But it will find its way back to equilibrium, but it won't find its way back to the same equilibrium you had before because you introduced a change. Does that make sense? So, just to give an example, don't write this, okay? Don't put your pencils down. I just want to draw it. Let's say that we had a reaction, a nice simple one, A plus B, or not A plus B, just the classic A becoming B, right? And let's say we did like we always do. There's A, there's B. Let's start with no A, or with no B rather, and we kind of do this thing. And then the B kind of does its thing and goes like that. But eventually they reach this steady state. All right, can you picture that? Now, let's say we all of a sudden, at this moment, we go in and we make a change. And we add a bunch more A. All right, so just in this moment, we all of a sudden add a bunch more A all at once. But we don't add more B. What's going to happen? The forward reaction is going to be favored again, right? Because our concentration of A just went up. So we're going to use that A up. And it will reach equilibrium again. But note what's happened. It reaches equilibrium, but the new equilibrium is different from the original equilibrium. Does that make sense? We reach a new equilibrium, but the new equilibrium is different than the old equilibrium. Does that make sense? And yes, our overall concentration of A has gone up, but it actually moved more in the direction of B, right? Does that make sense? Like, if you look here, we only have more A because we added more A. We didn't add any more B, and yet we end up with more B. We added more A, and the result is actually to make more B. Does that make sense? A little weird, but what it's saying is, whatever change you introduce, the way equilibria work, because by definition, the rate of a reaction depends on how much reactant is present, anything you add, the equilibrium system is going to try to, I'm anthropomorphizing it here, it obviously doesn't think, but the way the equilibrium works, if you add A, it's going to use up that A, and it's actually going to make more B. If you added more B, it's going to use up that B, it's actually going to make more A. If you add more reactant, the result isn't going to be that you end up with more reactant, the result is actually going to be that you end up with more product. It's going to shift it in the... And you know what I always think of it as? I have a really good analogy for this, I think. Anyone have a little kid in their life? Niece, nephew, brother, sister, cousin? Or even, they don't even have to be little, they can just be related to you, right? Anyone have a brother or sister? Because I happen to know, I have 2 kids, and like, if I had like heard my daughter saying like, oh, we're going to watch a movie tonight. I hope we watch like a Star Wars movie all day. So I know she wants to watch a Star Wars movie when they were little. And I was like, hey guys, let's watch a movie. What do we want to watch? And if Greg piped up first and was like, I want to watch Star Wars, Claire would be like, oh, anything but that. And then they would immediately start fighting and it would end in shouting and tears. Maybe this sounds familiar to you? Yeah? You like that with your sibling? Right? My sister could be like, I like chocolate. I'd be like, chocolate sucks. Even though I love chocolate. But so here's the point. You got a little kid you're trying to put the snowshoes on. You put the boots on, what are they going to do? They're going to take the boots off. You put a hat on, what are they going to do? They're going to take it off. Whatever you do, they're going to undo. This is Le Chatelier's principle, which basically says that's how a system at equilibrium works. Whatever change you introduce, the tendency is for the reaction to react to that by shifting in the opposite direction. Does that kind of make sense? So, let's actually look at that. So let's say we have A plus B in equilibrium with C plus D at equilibrium. All right? If we were to, hypothetically speaking, add more A, which way would the equilibrium shift? Would we produce even more A and B, or would we produce more C and D? Yeah. So the concentration of C would go up, the concentration of D would go up, and then what about the concentration of A and B? They would both respond by going down. They would undo the change that we introduced.
But we didn't do anything to the concentration of B.
I know, isn't that interesting? But it is still also a reactant. Does that make sense? So you can, to speed a reaction up, you don't have to add, or to make a reaction shift in the other direction, you don't necessarily have to add both of your reactants. You could just add one of them. That can be really helpful. Maybe one of them is really expensive, right? So you don't want to keep pumping it in, but then you've got another thing it reacts with along the way that's much cheaper. By adding the cheap one, you're going to use up more of your expensive one and make sure you're using it efficiently. You won't have it wasted by not reacting. Does that make sense? So if you think about this, you can start to control that. What if I could vent off, i.e. remove D? What if I could remove D from the vessel as we go? So the reaction's gone, it's at equilibrium, it's stopped, and it basically stopped, right? It's reached a steady state. And then I figure out, oh, all these are liquids, but D is a gas. So I'm going to vent it off. I'm going to get it out of there. What's going to happen? As we take D away, yeah, A is actually going to start getting used up. B is going to start getting used up. C is going to then, if A and B are getting used up, C will go up, and the concentration of D will go up, right? Because it'll go up. We made it go down. The equilibrium will respond by making it go back up. Whatever change you introduce, the equilibrium will tend to shift such that that change is counteracted, right? It's a negative feedback system. Yeah. Yeah. So just what I'm saying is, if I could artificially make the concentration of D go down, the reaction is going to respond by trying to undo that, by making it go back up. To do that, it's going to have to use up A, it's going to have to use up some B, and it will produce C, and it will produce D. The equilibrium will shift. No, if A and B are going down, then C and D have to go up, right? So by changing just one of these, by taking away D, I'm actually going to get most of that D back. That's how the equilibrium is going to shift. Maybe not all of it, but most of it back. But as a result, C is also going to have to go up because they go together, right? Where one goes, the other goes, which means these would have to go down. Does that make sense? Even though you only change one thing, it has to affect the whole reaction. So you can affect a whole reaction just by adjusting one thing. Yeah. If we were to graph this, okay, so this is going to be a little bit messy. But okay, we've got A, B. I mean, this is so messy. I don't know if this is even going to be helpful, but let's try, okay? Let's try it. So let's say that these were already at equilibrium, Okay, and we'll just arbitrarily pick values for them. We'll say, okay, there we go. Everything was at equilibrium. There they are. Okay, there they are. Now, all of a sudden at this moment, we're going to, what did we say we were venting off? D? Okay, we're going to remove D. All right, so we take this and we plunge it all the way back down here. Does that make sense? Well, now the equilibrium is going to shift because that means the concentration of this went way down. So the reverse reaction is going to slow down, which means that now the fast reaction is going to be the forward one, which means A is actually going to get used up, right? Because we're going to try to produce that D back. We're going to undo the change that we introduced, right? Which means D is going to get replenished. Now, as the concentration of D goes up, what else has to go up? Well, C has to go up. They live together, right? What has to go down? A and B. And so we actually created a new equilibrium state. And in the new equilibrium state, C and D are even higher than they were before. And A and B are even lower than they were before. We created a new equilibrium by introducing a change. Because whatever change you introduce, the equilibrium shifts to countermand it, to undo it. Was that helpful at all? Okay, we'll leave it there then. What if, I don't know. I think another example wouldn't necessarily be more clear, but let's say one out loud. While this reaction's happening, let's say I massively increase the concentration of C. This reaction vessel is here, and I go and I dump in a bunch more C. What's going to happen? So I make the concentration of C go up. How does the equilibrium respond?
E and A go down, C and D go up.
No, if I add C,
Oh, C and D go down.
C and D will go down, which means that by adding C, I'm actually going to force the reaction to produce more A and B, which means C will go back down, probably not as low as it was before, but it'll go back down. But D will go down with it, which means D will go down lower than it was before, and A and B will end up higher than they were before. So by introducing a change, the reaction will shift in the opposite direction. And what you're going to hear as language is that this, both of these, would be, here's the language we use, shifts to the right. And shifts to the right mean that we get more product and less reactant. Does that make sense? On the other hand, like we just said, if I added more C, we would get a shift to the, if I added more C, that means that's going to go down now. That will also go down. This will go up. This will go up, which means we'll get more of these things. We call that a shift to the left. Does that make sense? That's kind of informal language, but it's the language that chemists use most often. Does that make sense? Because it's just so quick to say, like, oh, this reaction is going to shift to the left, which really means you're going to get an increase in the concentration of the reactants. So that shift to the left, shift to the right language, is language we kind of want to get used to. You're going to hear it a lot. Does that feel okay? Now, concentrations aren't the only things that affect rates of reaction, which means they aren't the only thing that are going to affect an equilibrium. What else affects the rate of reaction? Pressure. Yeah. So let's say we had some reaction here, and we had A, which is a gas, decomposing into B and two C's, both of which are gases. Does that make sense? Okay. Well, that means on the left side, we have a total of 1 mole of gas for every round of this reaction, right? On the other hand, on the right side, how many moles of gas do we have here? 3 moles of gas, right? 2 moles of C and 1 mole of B. But we know that PV equals nRT. It doesn't matter what gas it is. Pressure depends directly on how much gas. Now, if this has reached equilibrium, all right, this has reached equilibrium. If I were to increase the pressure, what would happen? So if this is at equilibrium and I increase the pressure. So before we answer with relation to our reaction, look at me. If I increase the pressure, the reaction is going to shift to decrease the pressure, right? Does that make sense? Look at me. If I make the pressure higher, Le Chatelier's principle tells us the equilibrium is going to shift so that the pressure gets lower again. Maybe not down as low as it was before. In fact, not down as low as it was before, but somewhere between the two. If I increase it, it's going to decrease. Now, look here. This particular reaction, shifting which way will lower the pressure? If we go to the right, will we get less pressure? Or if we go to the left, will we get less pressure? Look at the reaction. Think about it for a minute. And say, okay, if the reaction were to shift such that the pressure goes down, if we go to the right, we're using up 1 mole of gas to make 3 moles of gas. In other words, we're increasing the amount of gas, right? A net increase of 2 moles of gas. If I go the other way, I'm using 3 moles of gas to make 1 mole of gas. In other words, in the net, I'm using up 2 moles of gas. Which one of those things is going to make the pressure go down? Producing more gas or using more gas? Using more gas. So to use more gas, this has to shift to the left. So if we increase the pressure, the reaction shifts, I should say the equilibrium shifts to the left. Because 1 mole of gas is less pressure than 3 moles of gas. So by shifting less, it can produce it. We use this all the time. So we, as if I'm some industrial chemist. This gets used all the time in industrial chemistry, right? Because if you want to make a reaction happen in bulk, and it involves gas phases, you can control which way it goes by putting it in a high pressure system. It will go in the direction of the side of it that is less moles of gas than the other. On the other hand, if you put it in a low pressure system, it will move in the direction of the side that produces more moles of gas. So you can really control the equilibrium balance of a reaction, the efficiency of your reaction, by changing the pressure. This is why a lot of reactions are done under extremely high pressure. I mean, there's other reasons for that too, but this is a major one. You can control the shift in equilibrium. I suppose this should go without saying, but in this case, if I were to decrease the pressure, which way would it shift? Not shifts, but shifts. Shifts to the right. Right? So if I decrease the pressure, it's going to put it back up by increasing the output of B and C, because that's 3 moles of gas having used only 1. That one feel okay? That one's usually the weird one. That one gives people a bit of trouble because it's a little strange, right? Okay, now let's consider temperature changes. A temperature increase favors the endothermic reaction. A temperature decrease favors the exothermic reaction. So let's look here. Let's say that we have A is in equilibrium with B. Nice, easy one. But the delta H is negative 180.2 kilojoules. Is this reaction exothermic or endothermic? Is it releasing energy or absorbing energy? Yeah, this releases energy. In other words, which side of the reaction would energy go on? Yeah, go over here. Which it might be useful to actually write in there. Does that make sense? Because when you do that, then if we said, okay, what if we increase the temperature of the system? In other words, if we add heat to the system, which way is it going to shift? We add heat. If we add heat, the equilibrium is going to shift to try to do what? Remove heat. Which way does this have to run to remove heat? To the left. Very good. It's going to shift left. So the concentration of A is going to go up or down? If this shifts left? Up. Very good. The concentration of B will go down. This is another way we can control the rate of control the equilibrium state of a reaction. If you want to favor the endothermic reaction, right? If you want to favor the reaction that absorbs heat, backwards as it may seem, as long as you don't go under its activation energy, as long as you don't cool it so much that it can't happen, cooling the reaction will actually drive it in that direction, right? Oh, I said that backwards. Sorry, increasing the temperature will actually go it. And then if you want to favor the exothermic reaction, as long as you don't go under its activation energy, cooling it will actually favor the exothermic reaction, which is what we're going to write next. Sorry, I said that backwards. If we decrease the temperature, if we cool the reaction, which way does it drive?
To the right.
Yeah, the equilibrium will shift to the right.
So decreasing the temperature would be the endothermic reaction?
I said backwards. Decreasing the temperature is going to favor the exothermic reaction. It's going to favor it going this way, right? It's going to favor it going forward, which is exothermic. Yeah, sorry, I misspoke before. So in this case, that would actually cause the concentration. If this shifts right, it's going to cause the concentration of A to go down and the concentration of B to go up. That's right. Good. So,
How is it going to the right when we're decreasing the temperature?
because when we decrease the temperature, the equilibrium is going to try to respond by increasing the temperature. And in this particular reaction, which way increases the temperature? More to the right or more to the left? More to the right, because one of the products of this reaction is heat. So whatever change you introduce, Le Chatelier's principle tells us that the reaction system is going to go full little kid on you and try to do the opposite. You increase the temperature, it's going to try to decrease it. But if you decrease the temperature, it's going to try to increase it. And again, that's totally using anthropomorphic language, as though the equilibrium like meets as a council and says like, all right, Joe introduced a change, we're going to undo it. What it really is about is you're changing the rates of the reactions, right? Yeah. You don't add heat to one thing or the other in a reaction. The reaction system is a whole unit. Do you know what I mean? Like you don't have the ability to go into a thing where everything's all mixed together and pick out every little A molecule and say, okay, you speed up, but you B's, you stay the same temperature. When you increase the temperature, you increase the temperature of everything. And when you decrease temperature, you decrease the temperature of everything, right? It's a system. Is that what you were asking? And did my answer make sense? Okay. A note, catalysts as a rule, I should note that this is mostly true, but not always true. But generally speaking, catalysts speed up the rate at which a reaction starts. It will speed up initial states, but typically they don't cause shifts in where the equilibrium lands. They will let you get to equilibrium quicker, but they don't actually change the equilibrium point. So mostly increase initial rates i.e. get to equilibrium sooner, but don't change the equilibrium K value. Now, again, that is not always true, is my understanding. All right. Yeah.
For this example, for the temperature change, we did exothermic reaction. What if we do endothermic reaction and we increase the temperature?
Well, an endothermic absorbs temperature, right? So if you increase the temperature, the reaction is going to try to respond by decreasing it. And since it's an endothermic reaction, the forward direction is going to decrease the temperature. So in that case, it would respond by favoring the right side. It would shift right because the right side decreases temperature, which is the opposite of the change you
Wouldn't it be
introduced.
like endothermic on the left side? The temperature goes on the left side. So,
Well, not temperature, the heat, right?
oh yeah. So
That's right. So it's not going to favor the right side because that would make more heat. If you increase the temperature, it's going to favor the side of the reaction that is not heat. Right? Right? Okay. Nobody else write this. So if you had A plus heat yields B, right? Okay, in equilibrium, and you increase the temp, okay, it's going to try to decrease the temperature. It can't shift left. Shifting left would make more heat. We don't want more heat, so it's going to shift right. Does that make sense? Okay, everyone else ignore that. Stuff's weird, right? Like you really do have to kind of think your way through it. But with these three, just with these three things, we can really dramatically control where an equilibrium will land, where a chemical reaction will land. For example, we have never really talked about equilibrium before, so I've always done reactions with you that go to completion. A few lessons from now, we'll learn about why it is that the types of reactions we've done so far, by and large, just keep going instead of coming to a state of equilibrium. For example, a reaction that produces a gas in our lab and produces bubbles that just go up into the air, that concentration can never build up because it's just floating away, right? So that's a kind of reaction where you're always taking away the product. So the reaction will just keep shifting to the right. There's lots more things like that. So play with that. There's some homework here. Make sure you get all done. I can't stress enough, guys. Look at me. I know we're all busy. I know we're coming up on the holidays. I know this or that. This unit's going to come fast. All right. It's just the nature of where we landed schedule-wise. We just don't have spare days to spend. So this unit's going to come fast and hard. So I need you to be on the ball and like dialed in. All right. This is take it serious time if you want to do well. And of course you want to do well. Why wouldn't you want to do well? All right.
this one, you know how for the pressure it was normal, but it shifted it.
Would you do me one favor? Sorry, I'm just